Hello my dear friends, hope all of you are doing well by keeping yourself safe. So today in this video I will start by describing when both the electric and the magnetic field is acting on the charged particle. So we will start with the concept of the velocity selector and we will try to understand the concept hidden behind it. So our first topic for today is the velocity selector. It is also known as Wien's filter. So the velocity selector is also known as the Wien's filter, and which is the device where a perpendicular arrangement of both the electric and the magnetic field are present. We know that in presence of both the electric and the magnetic field, when they are perpendicular to each other and also to the velocity of the charged particle, the force acting on the charged particle we can get to know from the Lorentz force, that F vector is equal to the force due to the electric field and the force due to the magnetic field is equal to Q times E plus V cross B. So we can see from this diagram, suppose I am taking the velocity of the charged particle is along the x direction and the electric field is acting along the y direction and the magnetic field is acting along the z direction. So the E vector is equal to E times j cap, B vector is equal to B times k cap, and V vector, the velocity of the charged particle, is equal to V times I cap, where I, j, k are the unit vectors along the x, y and the z axis. So Fe will be along the y axis, the force due to the electric field, that means Q times E. And the magnetic field will be both the perpendicular to the velocity and the magnetic field, so it will be minus Q Vb times j cap, so it will be acting minus y axis. So the electric field is acting along the y axis and the magnetic field is acting along the minus y axis. So now if we add up these two forces, that is the force due to the electric field and the magnetic field, you can see F vector is equal to Fe plus Fb, so it becomes Q times E minus Vb times j cap. So now we can see that in this case the electric and the magnetic forces are in opposite direction. We can adjust the value of E and B in such a way, I mean the magnitude of the electric field and the magnetic field in such a way that the magnitude of the two forces become equal and there will be no net force acting on the charged particle. The charge will move in the fields undeflected. So this happens when there will be no net force on the charged particle, so F becomes 0. So I mean this quantity becomes 0, Q times E minus Vv is equal to 0, or V is equal to E by B. So it is the ratio of the magnitude of the electric field and the magnetic field. Thus we can use the condition and select the charged particles with a particular velocity out of suppose a beam of the charges, and only those charges having the velocity of the ratio of the E by B will pass the region of the crossed electric and the magnetic field undeflected. So this setup is known as a velocity selector. So now we are going to discuss the generated magnetic field due to a current carrying wire. We will try to study the relation between the current and the magnetic field as the charge produces or the current produces. So this is known as the Biot-Savart law. So from the figure we can see, this is a figure that the infinite wire xy, this xy is an infinite wire and it is carrying the current I. We consider one infinitesimal length dl. You can see this is a very small element length of the wire, it is dl. It is a vector quantity because I am taking the direction of the dl along the moving of the current. So the magnetic field, we need to determine the magnetic field dB that is produced due to such small element dl at a distance r away from the dl. So at the point P, at a distance r away at the point P, we need to find the magnetic field. So the angle between dl and the displacement vector is theta. So dl is I'm taking in the upward direction and this is r vector, so the angle between them is theta. Then according to the Biot-Savart law, we can write that dB, the magnitude of the magnetic field at a point P at a distance r away from dl, what it will be, dB is proportional to I, the magnitude of the current, dB is proportional to dl, the length of the dl, dB is proportional to sine theta, and dB is inversely proportional to 1 by r square. So altogether we can write it as a constant, dB is equal to mu 0 by 4 pi, it is a constant, ideal sine theta by r square. So in the vector form we can write it like dB is equal to mu 0 by 4 pi I times dl cross r divided by r cube, where mu 0 is called the free space permeability and mu 0 by 4 pi, it has the value of 10 to the minus 7 Tesla meter per ampere. So the direction of the dB is both perpendicular to the dl and the r vector. So finally, from the above discussion, we have seen that this law can be used to calculate the magnetic field to a current element. However, this rule also can be used to evaluate the magnetic field due to some conditions like a rotating wire, a disk, and the line segment, etc. So now we are going to calculate the magnetic field due to a straight current carrying wire of finite length. So you can see from this figure that AB is a wire of finite length, and we are considering a small element dl that is mentioned here of EF. You can see from the figure. So EF has the length of dl, and we are trying to calculate the magnetic field at the point P due to the complete wire of length AB. So now we can see that for a small length of EF, that is a line element of EF, magnetic field at point P can be written like dB is equal to mu 0 by 4 pi I dl sine theta over r square, where the sine theta is the angle between the dl and the r vector, or better to say the ideal and the r vector. Now from the figure you can see that angle QEP is equal to theta. So angle QEP is equal to here theta. So I need to find the angle between ideal and the r. So it will be 180 degree minus theta. So I need the angle of FEP. So FEP, so it means 180 degree minus theta. So this is the angle between ideal and the r. So therefore dB becomes mu 0 by 4 pi ideal sine of 180 degree minus theta divided by r square. So it becomes mu 0 by 4 pi ideal sine theta by r square. So now from triangle EGP, angle G is equal to 90 degree. You can see from this figure, angle of EGP, angle D, this is equal to 90 degree, and this angle is d phi. So we can take it as much small as we can consider. So d phi is very much small, so it can be negligible. So this angle will be also 90 degree, because this is 90, this is negligible, so this obviously must be 90 degree. So angle P is equal to d phi is very small, so angle E is equal to 90 degree. So you can consider this angle also, angle DFE, this is also theta. So now this is just simple calculation of triangle EGP. EG by EF is equal to sine theta. You can see from this figure, EGP, this angle is 90 degree. So this is theta. So this is d phi. So what it becomes, that EG by EF is equal to sine theta. So EG is equal to EF sine theta. F is equal to DL. So it means DL sine theta. From triangle EGP, EG by EP is equal to sine of d phi. We can take d phi very small. So it becomes EP sine d phi. So EG becomes R d phi, because EP is R, and sine d phi can be written as d phi because if the d phi is very small. Now I can equate this to EG values. EG is equal to DL sine theta is equal to R d phi. So then dB becomes, the elementary magnetic field becomes mu 0 by 4 pi I dl sine theta by r square. It becomes mu 0 by 4 pi I put the value of dl sine theta as R d phi, so it becomes mu 0 by 4 pi I d phi divided by R. So now from triangle EQP, you can see from the figure EQP here that this angle is theta, so it becomes R by R is equal to cos theta. So we can write that R is equal to R by capital R by cosine theta. So dB becomes mu 0 by 4 pi I d phi by R. If I put the value of the small r here, so it becomes mu 0 by 4 pi I d phi. I put the value of small r as capital R divided by cosine theta. So it becomes mu 0 by 4 pi capital I by R times cos phi d phi. Now if I integrate from, you can see this is the final limit of theta of phi 1 to phi 2. If I integrate it over the total range of phi, so it becomes like B is equal to mu 0 by 4 pi capital I by capital R. So just I like to mention that capital R is the perpendicular distance from B to the line AB, or better to say the current carrying wire of finite length of AB. So this is the perpendicular distance, and it is the minimum distance from the point P to the AB. So if I integrate it, it becomes B is equal to mu 0 by 4 pi capital I by capital R phi 1 to phi 2 cos phi d phi. So it becomes mu 0 by 4 pi I by R sine phi 2 minus sine of phi 1. Now you can see that the length AB is infinitely long, so we can consider phi 2 as 90 degree. It is almost 90 degree, and phi 1 is in the if I consider the direction of the rotation of the angle, so phi 1 becomes minus 90 degree. So it becomes, so for the conductor of the infinite length, so phi 2 is equal to 90 degree and phi 1 is equal to minus 90 degree. So it becomes, if the conductor is of finite length, so the magnetic field becomes mu 0 by 4 pi I by R mu 0 1 minus of minus 1, so it becomes mu 0 I by 2 pi r. So this is the expression of the magnetic field for the uncarrying wire of infinite length. My friends, I'm concluding my today's discussion here. If you are new in this channel, please do like, share and subscribe our channel Invisible Threads, and make your valuable comments in the comment section of this video. Stay tuned and keep supporting us. Thank you.